Now with vectors, we can do vector operations such as sum or scalar multiple, and such as a new vector by this linear combination of two vectors, u and v. As you can see, this 2u plus 3v, we can name it as w, for example. This w vector is in terms of two vectors, u and v. So I mentioned how we got this 2u plus 3v, right? As long as this u and v, the u vector and v vector given, and 2u is just twice as u, 3v is 3 times long as v, and this, you see we can show them in, we can visualize them, and then formulate parallelogram, and then the diagonal will be 2u plus 3v. And this, if we call it this new vector w, then w is represented by u and v as a linear combination of u and v. So linear combination is a terminology that in this case, w is a linear combination of the two vectors, u and v. Scalar multiple of u plus a scalar multiple of v, and to generate w. So with this example, we can look at a general definition. Linear combinations of vectors. So we call this vector u a linear combination of these vectors. You see, we can use more than two vectors, right, to generate a vector. So in the example I show you is a w vector, which is generated by two vectors. But now we can define a general definition. We call it a linear combination of p vectors. How many vectors here? P vectors. v1, v2, vp. P can be 2, just v1, v2, right? P can be more than 2. So that is a number of vectors in the n-dimensional space Rn. That means they are vectors of n entries. So each vector is a vector of Rn. And if we do a linear combination of the p vectors, that means scalar multiple of each vector, right? And then after you get that, then you add them. That is a linear combination of p vectors. If u can be represented by such a linear combination, then we say u is a linear combination of the p vectors, v1, v2, vp. So that means if there exists the constants c1, c2, cp as coefficients of those vectors, v1, v2, vp respectively, and u can be written in this form, then we can claim that u is generated by these p vectors, or u is a linear combination of the p vectors. Right, so that's the definition. So once we are clear about the definition, note that the very important thing is there exists values, the constant multiples, such that this is true. So if that's the case, then U is a linear combination. So once we are clear about this, then let's try to use a number of vectors to generate some vectors. So it seems if we know some vectors, we can just simply let's generate some vectors. That means we're going to go from here to generate some vectors. So a very simple example is that we can simply use the R2. Let's pick a very simple vector, which we call it E1, a unit vector in R2, 2 entries. It's a unit vector. And I can pick another unit vector in R2. So with these 2 unit vectors, let's say twice of the first vector plus 5 times the second unit vector. Let's see what we get. It's a linear combination of the 2 unit vectors, right? If we write it more specifically, which is twice of this vector plus 5 of the other unit vector. And we can see this is simply 2, 0. And the other one is 0, 5. And together we get 2, 5. So in this example, we notice that 2, 5 is a linear combination of the 2 unit vectors because there exists constants or coefficients for these 2 vectors such that the linear combination is equal to 2, 5, the vector 2, 5. So then we can say 2, 5 is a linear combination of unit vectors, E1, E2. Because we just generated the vector 2, 5 using E1, E2. So it's compared to the previous definition. So it's like we used 2 vectors generate 2, 5. Now we can easily generate more vectors. If you want, just change the coefficients. Let's think of some more vectors. So here is another vector. So let's say 10 times E1 and then plus a negative 10 times E2. It's another linear combination of the 2 unit vectors. And then what do we get? Just think, this number will change, right? It will become 10. This will be negative 10. So what happens? So as a result, we get 10, negative 10. So you see the 10, negative 10, this vector is also a linear combination of the 2 unit vectors. Now, can we do some more? Yes, we can just change the coefficients. Let's generate more vectors just to see how easy we can generate another vector using the 2 unit vectors. So let's change the coefficients. So if I change the coefficients, such as 0 times the first unit vector and 7 times the second unit vector. So now, yeah, instead of the instead of the E1, E2, yeah, just show you this is the E1, right? It's often convenient to give a name. As you can see, with time, you will recognize this is a 0 times the vector 7 times second vector. So I can write more specifically this way. And 0 times the first vector is going to be a 0 vector. 7 times the second unit vector is that. So together is still 0, 7, because 0 vector add any vector is still that vector. So 0, 7. So that means 0, 7 is a linear combination of the two vectors. Also, now I want to ask you, how about 0, 0? Is 0, 0 a linear combination? The question is, that is 0, 0 a linear combination of E1, E2. So E1, E2. We're talking about R2, right? The vectors in R2. So as we recall, R2 means each entry is a real number with two entries. So E1 is that unit vector just given. E2 is the unit vector given. So to determine this, to answer this question, is the 0 vector a linear combination of E1, E2? So let's put a 0, 0 here. The question specifically means, is this vector a linear combination of E1, E2? That means, can we possibly find the constants in front of E1, E2 such that the 0 vector is represented by the two unit vectors? So I just translated the question into a different form. So what we are trying to determine is that, is 0 vector a linear combination of E1, E2? That means, is 0 vector representable by E1, E2 with this form? That means, can you find C1, C2 such that this combination will produce the 0 vector? Okay, so, and try. And this is a question, if we write, then we can quickly realize that we can write this C1 times first unit vector is this vector. C2 times the other unit vector is this vector, right? So if we add them together, we are trying to determine, is this possible? Can we possibly find C1, C2, those numbers, to make this true? So I translate again. So it's an analysis to make it maybe possible for us to determine. So this, again, if you add, because essentially we're comparing two vectors, is 0 vector equal to the other vector, the sum of the two. So let's say the sum is C1, okay, the sum of the two vectors is actually C1 plus 0, 0 plus C2. So this vector, is it possible? Yes, possible, as long as C1, just when we compare, we see that it's possible to find a solution that as long as the C1 is 0 number, C2 is also 0, then we know immediately that, yeah, by solving this, and all we need is to put a 0 here, 0 here. okay, 0, 0 for C1, C2, then we can, so this is a 0, that's also a 0, then we can generate a 0 vector. So yes, 0 vector here, this 0 vector is a linear combination of the two unit vectors. Okay, so far we have picked quite a few vectors in R2, and we show that they can be represented by the two unit vectors. Can we get a real arbitrary one? So let me give you a vector in R2. Suppose I have a vector, let's call it AB, because A can be, it's just a certain number, right? It can be any number. B is any number. They are not necessarily the same number, AB. Yeah, but each one is a real number. So this is a vector in R2. My question is AB a linear combination of E1, E2? This vector in R2, is AB a linear combination of the two vectors, unit vectors, E1, E2, and E2? So it's a generalized question. We know that when A is 2, B is 5, 2, 5, right? Well, is a linear combination of unit vectors. And then we tried when A is 10, B is negative 10. Yes, we saw it. We can easily generate a vector using unit vectors. But now, as arbitrary as this, AB, yeah, A is a number, B is a certain number also. Yeah. So then can we generate the AB using the two unit vectors? So if we so we can answer this question, just try to formulate this question is essentially to ask, can we write AB as this form, E1, E2? And can you possibly find C1, C2, or just and then, yeah, because they are to be determined, I want you to, we can put X1, X2. Can you put some numbers, right? So those, so far in the definition, we call C1, C2. You can write it as X1, X2 if you want. Just determine the coefficients. Can you generate AB? Yeah, it doesn't hurt if you change the name to C1, C2. So it's X1, X2. They're essentially the same problem, right? So can you find C1, C2? And based on our previous experience, we can say, sure, if we put the C1 as A, if C1 I pick as A, C2 if I use as B, then it will be this vector. No matter what vector it is, we can generate the vector using the unit vectors. You see? So this is a very arbitrary vector, and we can still using a linear combination of the two unit vectors. So this also means that we always have solution to a system. So for whatever AB we choose, and we can always find a solution, right, for the system, C1 and C2. Because this system is, after you do this, the right-hand side is simply C1 and C2, we try to make it satisfy this equation. So C1 has to be the same as A, C2 has to be same as B in order for this true. And certainly we can find values for C1, C2. Okay, so with that experience, let's try another. So this next question is so this question is linear combinations. So given a vector u, which is in R3 now. So R3, although it has more entries, yeah, but the reasoning, the method is the same. So u is this. The question is determine if the vector u can be represented as a linear combination of v1 and v2. Yeah. So we want to decide if u can be a linear combination of v1, v2, the two vectors. So v1 is 1, 2, 4, the vector. v2 is 2, 5, 1, the vector. So more specifically, you want to know whether this given u, whether this vector u is a possibly, can this u be written into a linear combination of u, v1, v2. v1, v2 are the vectors given. So u is given, v1, v2 are given. So only thing to determine is, can I possibly find scalars, right? Scalars. Or in the previous definition, we use C1, C2, but here they are to be determined. Can I possibly find those scalars so that this satisfy this? If you can, then u can be generated by the two vectors, v1, v2. Otherwise, u cannot be represented as a linear combination of v1, v2. So either or, the answer is either yes, can be represented by a linear combination of v1, v2 if we have solution to the system, right? Or no, if we do not have solution to the system. So let's try to solve this. What should be the x1, x2? Can we possibly find values for x1, x2? Okay, so once you do the scalar multiple, you see that each entry times x1, you get this vector. Each entry of v2 vector times x2, you get this vector. And then we're trying to decide if this, can we possibly find x1, x2 so that the sum of two vectors is equal to the u vector. So then let's just add the two vectors. So this is a sum. So here from this, you just compare two vectors. Essentially, we want to see whether x1 plus 2x2 is equal to 8. x2x1 plus 5x2, 19. 4x1, x2 is 11. We want to compare the two vectors. Can we find x1, x2 such that this equals 8, that equals 19. The last entry is 11. So to make sure the corresponding entries are equal. So then we see three equations. That means we just try to determine x1, x2 for the system, right? So because their corresponding entries are equal, then we are trying to determine x1, x2 of this system of three equations. So that's not new. We know equation form, but you see, the original question was a question related to the vector relationship, but now it is a system of equations. Yeah. So to determine, and then we can go ahead, write the augmented matrix. And once the augmented matrix, once we do the replacement to the second row and third row, we can reduce this entry to 0. And then we can again use multiple of the second row to eliminate this entry, -7, to make it 0. So then eventually we end up at a reduced matrix. And that reduced matrix means 1 times x1 is 2, first equation. 1 times x2 is 3, second equation. The third equation is just 0 equals 0, which is always true. So reduced to this, and then we see we can find a unique solution, 2 and 3. It doesn't matter if it's unique or not. At least we have a solution, 2 and 3. So this means as long as the system is consistent, you see, from here we see the system has at least one solution, right? As long as it's a consistent system, then we can say we can find solutions. That means there is at least one solution to this problem. Here we find x1, x2, and 3, 2. At least one solution. Or even if you have many solutions, that's fine. You all need is to have such at least one solution. So all we need is to determine the consistency of the system. So if it's 3, you can verify quickly. So 3 times 1, 3. 2 times 2. I mean, x1 is 2. x2 is 3. Yeah. So that's right. 2, 3. So if it's 2, 3 times 2 is 6. That's 8. Yeah. And then also 2 times 2 is 4. 3 times 5, 15, that's 19. So you can check, right? So you can double check once you get a solution. So as you realize the vector equation here, you see one vector is a linear combination of two vectors. And we're trying to solve a vector equation. So this indicates, but then this vector equation is equivalent to a linear system. Yeah, the vector equation is equivalent to this as well, then reduced to the linear system. So we can recognize a vector equation can be written into a system whose augmented matrix is this. So let's just quickly wrap up the vector equation. So if we have such a vector equation, let's write the augmented matrix. The first rule will be 1, 2, 8. Second rule will be 2, 5, 19. The third rule will be 4, 1, 11. Yeah. because the third equation is 4 times x1 plus 1 times x2 equals 11, right? So yeah, the second equation will be 2 times x1 plus 5x2 is 19. The first equation is 1 times x1, 2x2 equals 8. So that's why we have a system whose augmented matrix is this. So very easy. Once we go through this one example, you have more clear understanding of the vector equations like this is equivalent to a linear system. And also, so this different forms, right? Vector form so far from this lecture. And the equation form we saw at the very beginning of the course. And the augmented matrix form, that's just representing the same system. So 3 forms. Okay, so today you just, from this video, you learned the vector form of a system. So in summary, so I want to introduce one more quick terminology. That is, if there is a vector u and it's a linear combination of p vectors, that means we can find a solution, right, to this system. If there exists at least one solution to the system, then that means we can find the values for these coefficients, x1, x2, xp for these p vectors, so that the p vectors linear combination can produce u. So if there is at least one solution to the system, then we say this, yeah, so U is a linear combination. So that's the vector form. The vector form is linear combination of those vectors equals another vector. So this is the vector form. In the augmented matrix form, you just simply put each vector V1, V2 as columns of the augmented matrix. And U is the last column. So that's a matrix with how many columns? Total of P vectors plus U, right? That's P plus 1 columns. Yeah, so the system has augmented matrix in that form. So you just see the equivalence of this problem and this. They are just representing the same, but the same system, but they look different. So now see the connection is important. So that's the new form, the vector form for the system. And a terminology called span. Span. So if U can be generated by the set of vectors, then we say U is in the set spanned by the P vectors. So this span means all the vectors U that could be generated by this P vectors. So it's a set. It's not just the set of P vectors. It is including all the vectors U that could be represented, could be written as linear combinations of these P vectors. So with the span, it is very different than just this. So without span, it's just a set. of p vectors, right? With a span, that means all the vectors that are generated by these p vectors, whatever vectors. So that means it's a set that include, many vectors. We will get more understanding of this. So if I ask you this question, is AB the vector in the span of the two of is the vector AB in the span of E1, E2? Then what we have to do is to decide whether this AB can be generated by the E1, E2. And we know the answer is yes. Right? So for whatever AB in R2, we can always generate AB using these two vectors. Yeah, so more specific is if A is 2 and 5. Remember, if is AB, for example, is 2, 5 in the set spanned by the E1, E2. E1 and E2, right? So if we want to answer that, then we will say, okay, let's see if 2, 5 can be represented by the two unit vectors, E1, E2. And we know answer is yes, because if I put 2 here, if I put 5 here, yes, 2, 5 can be generated by unit vectors. Therefore, 2, 5 is in the set spanned by the two unit vectors. So in that case, we just say 2, 5, this is or belongs to the set spanned by the unit vectors. Okay, so the span, means that all the set that can be generated by these given p vectors, right? So, so that's the definition of span. So that's a new term, has a very precise meaning, and it is to show all the sets generated by the two vectors. Yeah. All right. So we can say we can also use span, the set of all vectors generated by a certain set of p vectors. Okay, that's all for now.